So this is this was an example I conceived during the past weekend. So this is a very interesting example, which can demonstrate multiple crucial concepts in linear algebra in a unified fashion. So let us consider a 2x2 matrix. Oh, let me share the screen. Can you see my screen?
Yeah.
Okay.
Yes, we can.
All right. So okay. So now let us consider the matrix A, which is 2 epsilon squared, 1 and 2. Okay. So this is the 2x2 matrix, which is easy to solve. And now let us find the eigenvalues. So A minus lambda I determinant. So this is a 2 minus lambda squared minus epsilon squared, which is lambda squared minus 4 lambda plus, we have a 4 minus lambda, epsilon squared equal to 0. So now we have two solutions, which I call lambda plus or minus. So this is going to be 2 plus or minus epsilon. So here, epsilon is a real number. It can be any value. So we have two eigenvalues, and for lambda plus, which is 2 plus epsilon, then we can solve the eigenvector x1, which is epsilon 1, and lambda minus 2 minus epsilon. Then we have so this, let's call this x plus and x minus, and this is minus epsilon and 1. So everything's goes quite smoothly. And then we can plot the eigenvectors, and we want to normalize it. So this is going to be 1 over square root 1 plus epsilon squared, and so is this one. Then if we plot it, let's say this x and y, then these two eigenvectors, let's draw a unit circle after normalization. So this is a unit circle. And let's say if epsilon is positive, right? For positive epsilon, then this is my x plus. Yeah, and then this is my my x minus. Okay. So then we can define the matrix of eigenvectors S by treating x1 and x plus or x minus as the two columns. Then it diagonalizes A through similar transformation, right? So it becomes 2 plus epsilon, 2 minus epsilon. And then we have 0, 0. So there's no problem at all. Then what is interesting is that when epsilon goes to 0, then lambda plus and lambda minus coincides with each other. So now we have a degeneracy, right? And now because this is a 2x2, so as we had introduced in class for 2x2, once we have a degeneracy, then the matrix is also defective and non-diagonalizable. So there's going to be a problem in the diagonalization when epsilon goes to 0. And in this case, A becomes 2, 0, 1, 2. And this is a defective matrix. But there's no problem for solving the eigenvalues. We can just go ahead and solve the characteristic polynomial now, which is lambda minus 2 squared equal to 0. So we have a single lambda. So, or in other words, lambda plus equal to lambda minus equal to 2. But if we inserted it back into a minus lambda, then a minus lambda I gives us 0, 0 on the diagonal positions, right? And then we have 1 and a 0 here. Then if we want to solve the x1 as a1 and a b1, we set it to 0. Then the first equation gives us nothing, just 0 equals to 0. The second equation gives us, a1 equal to 0. And there's no restriction on the choice of b1. So b1 can be anything. Then, then we can choose the normalized eigenvector x1 to be just because the first element must be 0. Then if we want to normalize it, we just set b1 equal to 1. So this is the a choice of normalized eigenvector. But that is the only eigenvector that we can find. There's no second eigenvector, even though lambda repeats twice. So then we need to go to the generalized eigenvector by solving the a minus lambda I, the same thing. And now we give it an x2, which is a2 and b2, and let's give it a tutor to differ from the ordinary eigenvector. And we want to set this guy not to 0, but to x1, to 0, 1, which we had already written down. So this also gives us that a2 tutor equals, well, this time it is a2 tutor equals 1. And there's no, it says nothing about b2. So b2 tutor can be anything. And again, we choose, we would like to make a simple choice. So we would like to just make b2 tutor 0. So x2 tutor, the generalized eigenvector, can be chosen as 1, 0. But we should be bearing in mind that it can be 1, let's give it a c. So c can be anything, right? This is the general choice. And then if now we go back to this figure and draw the generalized eigenvector, then let's see what they look like. For x1, it is 0, 1. So let's call this is x1. So the 0, 1 is pointing here after normalization. Okay, so this is x1 when epsilon goes to 0. And you can also see that if we continuously vary epsilon and set it to 0, then these two eigenvectors will continuously fold it until they become x1, right? They will continuously fold it towards x1. And right here, these two different eigenvectors now becomes the same one, the same thing. Then the generalized eigenvector x2 suddenly pops up. So now this is 1, 0. So once x plus and x minus, they continuously fold it towards x1, then right at this point, a new generalized eigenvector, which is x2 tutor, pops up. It points to be here after normalization, right? But I mean, actually, it can be anything. It can be, because we can choose an arbitrary c, then after normalization, if we want to give it 1 over 1 plus c squared, then unless c is infinity, then, the choice of x2 tutor can be anywhere in the first and the fourth quadrant, but just not include the y-axis. So here, this is going to be very interesting. So when epsilon goes to 0, the ordinary eigenvector x1 is pointing in the y direction, while the x2 can be any choice, in the first and the fourth quadrant. So x2 theta can be anywhere in this region, right? So that is the geometrical geometrical meaning of the generalized eigenvector. And then now we can define the matrix M. So x1 and x2 in this order, then this is just a 0, 1 and a 1, 0, right? But let's say here can be anything. It can be C. So this matrix, through symmetry transformation, can send A into the Jordan canonical form, which is the two eigenvalues, 2, 2, and there's one missing eigenvector, so 1 here, right? This is the Jordan canonical form. Okay, I think that is the case for the Jordan canonical form. But then the problem can have a further generalization. So now, having seen the special case when epsilon goes to 0, then we could also see what happened when epsilon go to 1, or plus or minus 1. So epsilon square goes to 1. In this case, the matrix A becomes 2, 2, and epsilon squared, which is 1, and here is another 1. So now this is a symmetric. So we know that for symmetric matrix, it is guaranteed to be diagonalizable. Wait a minute. So yeah, right. So at this point, we have a two eigenvalues. Lambda plus is 3, and lambda minus is 1. And then the corresponding eigenvector x plus is 1, 1, and x minus is minus 1, 1. Okay, and because now H is symmetric, so x plus and x minus, they are orthogonal to each other. This is a guaranteed property. And at this particular point, if we make the SVDs, then the SVD now reduces to the eigenvalue decomposition, or simply put it, eigendecomposition. So here I'd like to make an additional comment. For SVD, you can always do it. It always exists for arbitrary matrix. And in general, the SVD is not the same as eigendecomposition. But when A is emission, or generally it's not A emission, I think generally when A commutes with A emission. So when the matrix is normal, no, let's see. No. I think this is not the same. So we still have to have an emission. So once A is emission, or it's a symmetric in the real cases, then the SVD reduces to eigenvalue decomposition. Because in this case, the A emission must be the same as A emission A. So when you solve the matrix U and V, they are exactly the same. Then U sigma V becomes U lambda U dagger. Okay. And like I just made in the corrections at the beginning of today's class, so when A commutes with A emission, this is equivalent to the unitary diagonalization condition, right? But in general, this might not be true. And actually, we can see this. So let's say now if I would like to calculate so now let me write A again. So 2 epsilon squared 1, 2. We can check it. So A emission, or simply A transpose, because this is a real. If we calculate A transpose, this ends up with a 4 plus epsilon fourth, 2 plus 2 epsilon squared, 2 plus 2 epsilon squared. So this is a symmetric matrix as expected, but A emission A is different. So it's easy to observe that the diagonal elements, switches order when we compare and AHA, right? So unless epsilon equals 1, this condition does not met, right? Only at epsilon equals 1, then we could have this. And we see that the particular point of epsilon equating 1, that is where A becomes emission or symmetric. And in that particular point, this SVD reduces to the eigendecomposition. And A is unitarily diagonalizable. So we know that, at the beginning of this problem, we solved the diagonalization problem for arbitrary epsilon. But for arbitrary epsilon, obviously, A does not commute with A emission. So it is a diagonalizable, but it is not unitarily diagonalizable, right? So that is the subtle point. It is a diagonalizable through a non-unitary matrix. So I would like you to see an animations of this problem. Let me change my screens. Let me stop sharing here and share. Okay, this is my code. Okay, so this is the matrix A, and the assumption is that epsilon is positive. But I would like to encourage you to try when epsilon is an imaginary number. They're going to be more interesting. But we have no time to discuss that complicated case in class. So this is the 2 eigenvalues in terms of epsilon. So when epsilon equals to 0, the 2 eigenvalues coincide and the system becomes degenerate. And this is the singular value decomposition. And you can verify that when this epsilon goes to 0, then yeah, the singular value decomposition was successful. But when this is not 0, for example, if we give it a very small number, then you will see, well, there are gonna be some computational errors from the computer, right? And here we would like to extract the matrix of singular vectors. So the singular values. The singular values in terms of epsilon, this can be complicated. But when epsilon goes to 1, the very special point where the two A is symmetric and unitarily diagonalizable, you see that the 2 singular values are the same as the 2 eigenvalues, right? So this is very interesting. So at this point, let me make an annotation. So at this point, A is 2, 1, 1, 2. So if you solve the eigenvalues, it gives you lambda plus equal to 3, lambda minus equal to 1. But if you make calculate the singular values is also the same. So at this particular point, SVD reduces to the eigen decomposition. Okay, and then in general, the AA transpose and A transpose A are not the same unless epsilon goes to 1 or positive plus or minus 1. Okay, so now in the following, this is a plot of the eigenvalues, lambda plus, lambda minus, as well as the singular values, sigma 1 or sigma plus and sigma minus. And let's see what happened here. Okay, so this is really interesting. At epsilon, so this is the epsilon. At epsilon equal to 0, the two eigenvalues, lambda plus or lambda minus, they become degenerate. So this is the degenerate point. But at this point, the two singular values are not degenerate. And when we increase the lambda, and at the particular point of lambda when we increase the epsilon at epsilon equal to 1, the eigenvalues, the two eigenvalues and the two singular values coincide, right? We had just seen that. So at epsilon equal to 0, the system is degenerate, non-diagonalizable, but the singular value decomposition is still valid. And at epsilon equal to 1, the system becomes efficient, and the singular values and the eigenvalues are the same, and SVD reduces to the eigen decomposition. And if we further increase lambda, epsilon, then at another special point, epsilon equal to 2, then we see that here, sigma plus and the lambda plus, they are not the same. But the sigma minus and the lambda minus, they are the same. They become the same again. And they are both 0. And if you look at the fine structure in between, they are slightly different. So, well, if we continuously vary epsilon, then it poses the question that how can the eigenvectors and the singular vectors change, right? So that is the problem. And let's see that. Let's plot the eigenvectors and the singular vectors. So here, the mu is just epsilon. This is the epsilon. So let me drag this. Okay, let's start with a 0. So okay, at 0, so the two eigenvalues, the two eigenvalues are degenerate, so are the two eigenvectors. So this is x plus equal to x minus here. And then if we move away from 0, the two eigenvectors. So this is a unit circle, and the vectors should be understood this way, right? So I did omit the arrows just for visual clarity. So they are unit vectors moving on the unit circle. So okay, so once we move away from the degenerate point, the two eigenvectors changes dramatically. And these guys are the left and the right singular vectors. I forgot which is which, but the two blues ones might be the right singular vectors, and the orange ones are the left, right, whatever, so singular vectors. And you see that once we approach the point of 1, the singular vectors and the eigenvectors coincide, right? And then if we goes beyond 1, then the singular vectors and eigenvectors becomes different again. But, one singular vector and one eigenvector, and here are very close to each other. So that is why here you see the sigma minus and lambda minus are still very similar in the range between 1 and 2, right? In this range, sigma minus and lambda minus are still very similar, very close to each other. So that's why one singular vector and one eigenvector are still very close to each other. And when we move to the point 2, 2 is just, 2 is actually a singular point, because at the 2, A is 2, 4, 1, 2. And you calculate the determinant. This is a 4 minus 4, which is a 0. So that's why, the computer returns error. So 2 is actually a singular point where the A is non-invertible. But like I said, A is still diagonalizable, but it's non-invertible at epsilon equal to 2. And if we move away from 2, you see what you see here is that one of the singular vectors jumped discontinuously to the opposite side. And here on the singular values, you see here it has a discontinuous change, right? The slope is discontinuous. So this is a very interesting problem. We have 3 special points: the degenerate point, the emission point, and the non-invertible point. And by continuously vary epsilon, then we can see how the eigenvalue decomposition, the singular value decomposition are intrinsically related. And also at the non-degenerate point, we can define the Jordan canonical form, which I had introduced on the other screen. Any questions about this example?